Alright, making a draft science video. Kind of sloppy, but hopefully the point will be made. So anyway, hopefully you'll be able to see that little dot and the piece of paper and such. And so what I have here is just two diffraction gratings, and they have 500 lines. And unfortunately this height is a little imperfect. But anyway, hopefully you can see the two outer edges, fringes on the outside here, these out here, over there. And so these just two pieces of film, and I'm just sliding them across each other so they're coming in different angles. You know, I can slide them up and down and nothing will change. If I slide them perfectly straight up and down, you'll get very little change. And but if I do a little bit of an angle, then you can see them turn. So the point is, they're clearly, it's two separate patterns, and the dots are slightly smaller in the one set, so it's a little bit weaker. So clearly the light going through the center of the laser is being it's being diffracted a second time, just the center light primarily. So just pointing that out. Now if I turn them this way, you probably aren't going to see it. So now the two lines are crossed, and it's basically the same effect, except now the two patterns are like a square. You can't see the bottom dot. You might not be able to see the top dot. So whatever. You can see some of it, or you can't see some of it. But yeah. So the point being that these two layers are stuck right next to each other, and clearly the two aren't combining. They're creating two separate patterns, distinctly separate. One moves with one sheet, one moves with the other sheet. Not the same at all. I mean, not combined at all, anyway. So I just wanted to show you that. Lots of other bigger and better things to show, but that's it for now. Oh, I gotta undo that laser. Sorry, I'm gonna untape the laser. Spare the batteries and save the laser also, I imagine. So anyway, so last video I did make a slight error. Right what I said when, I said, I'm confident about that. I made one mistake. I said deceleration creates a blue arrow. So we're back to this thing. This is the essence of the universe. And deceleration is just the opposite. The red arrow is going to come in through the side here, hit the forward arrow, knock the forward arrow going that way, and it'll be releasing a red arrow. So the electrons only reflect, essentially deflect, create a 90-degree angle on red arrows, and the blue arrows that hit a blue will always just pen. Ugh. Come on, pen. Okay, the blue ones just do this thing. They just do the reflecting off the arrows of the electron. So the blues always just come straight back, no change in direction. The reds change direction. And essentially deceleration is just acceleration in a different in a direction opposite your primary velocity. Now, this might be really relevant to the two-slit and the entire subject of quantum mechanics, and the fact that there appears to be some random choice in terms of where something ends up going. Okay, so the idea would be, I'll try to represent it, I guess, with maybe just dots of force or something. But you could imagine that if I had something that had two elements to its so let's just imagine that these electrons is just full of a million of these little quanta. And let's just say I had 6 extra going this way more than we're going this way. So there's 6 extra. And there's 4 extra going this way instead of this way. Now the field is going to keep hitting it with the reflecting arrows from the blue ones, and also the red ones. So the red ones are going to keep trying to knock off any extra, because they're going to they're going to probabilistically affect the imbalanced ones more than the unimbalanced ones. Now let's say that you have a velocity, so you have 5 extra going this way. It kind of means you have 5, if they're truly extra, not just 5 more than the ones going backward, but you have 5 more than a neutral state. So let's just say if the electron was perfectly stationary, maybe there's a better way to say it, it would have 10 going in all directions. So it would have 10 going this way, 10 going that way, 10 going up, 10 going down, 10 going forward, 10 going back. So then I can just add to that. And so what I'm saying, it has 15 going forward. It has to subtract that extra 5 from left to right or up and down. But there's still going to be a balance, imbalance left and right and up and down. So what I'm trying to explain is that, let's just cut it to 2 dimensions. So there's forward and there's left, right. Forward, back, left, right. So we have 5 extra going forward. So we have 5 less side to side, which means maybe we could have 2 less on one side and 3 less on the other side. That means we have 3 on one side and 2 on the other side, which means there's a tendency to go in the 3 direction. But it's a weak tendency because it's only 3. It's actually 5 minus balance. So the angle isn't going to be between left and right. It's going to have 5 extra going forward. That means for every 5 steps it goes forward, it's only going to go 1 step to the right. Or let's say 2, just for the sake of argument. It's only going to take 2 steps to the right for every 5 forward, and it's only going to take 1 step to the left. So you can kind of see that it's going to have a tendency to move more in this direction, but it's not going to be splitting the difference. It's going to be more forward. So this angle, if you get what I'm talking about here, this angle is the variable angle. Depending on the acceleration of the electron, that is how fast it's moving forward, will dictate how much of an angle it's going to move at, how much it lost from its perpendiculars, and potentially how much the imbalance in those perpendiculars will affect this angle. So this angle can be variable, but it's always going to be quantized. It's always going to be some precise amount, a quanta, a Planck amount of angle. It's not an unlimited number of angles that are possible, it's a limited number of angles that are possible. Alright, so that could be really very relevant to the fact that the 2-slit experiment creates a broad pattern, is because it has to do with how fast the electrons are moving in proportion to how much side to side imbalance they have. So it's still a little bit of a complex equation, but I would argue the side to side imbalance is the thing getting affected by the slit width. So it becomes interesting and relevant and pertinent. Okay, so anyway, so somebody on this website here posted, well, first one guy posted a link to this in TED Talks, and I saw it, and I can only watch like 60% of it. First, they always do this thing with the face mic, and it seems like such a bad idea. Like somebody would have figured out by now that you can hear, like when they get dry mouth, and it's really. I know I have some problems. I have wet mouth. I mean, so I don't have perfect articulation anymore. Left over from the stroke, maybe, I don't know. Bad teeth, I don't know. Regardless, I don't talk as good as I used to. But so I mean, I'm not trying to be critical of the way the guy talks. I'm just saying, but putting those face mics on is just such a bad idea. And I'm just amazed they haven't figured that out yet. That it's really irritating to hear every swallow and sound. I find it obnoxiously obnoxious. So anyway, and then this theory is just insane. Yes, it's this crazy multiverse bullshit. It's just horrible. But yeah, it's just this, you know, physicists are religious kooks all the way. I mean, it really has just become a fairy tale all the way down. Alright, so anyway. So this was a antinatalist question. So this is the one here. Amendum, if light interacts with the material of the slits in the double slit experiment, different materials would produce different patterns on the wall. See, the trick with that is electrons are all the same. And no matter how dense the material is, the spacing of the electrons is always going to be the same. The electrons won't space differently. That's sort of a charge thing. And charge really doesn't have anything to do with the density of the material that's charged. So that's really not going to be a consequence. I mean, a narrow slit is a narrow slit. Now the trick is, what does seem to be true, is if you lengthen, that is thicken the slit, you'll destroy more of the light getting through, so that it appears that you're providing more opportunity for more electrons to exist in between the slits by having thicker slits. But that experiment hasn't really been done, but I'm saying it's intuitive. You can say that we kind of do know that if you make the slit material a foot deep, and with that very small hole, that a lot of electrons, a lot of photons, won't make it to the other end. It will degrade the light. But then it depends on the polish. If the surfaces are polished and very reflective, then the light will be fine. So it gets a little bit tricky. So anyway, but the point is this is about electrons. It's not really about the surfaces that they're interacting with. It's just about the nature of electrons. A spark is a spark. It doesn't care how thick the material is. The spark is going to be the spark, and it's going to be based on how many electrons are piled up on the end of the material. So it just doesn't, in my opinion, it doesn't matter. The electrons are going to space the same whether the slit's made out of a thin film of carbon or razor blades or, you know, a quarter-inch piece of plastic. Quarter-inch piece of plastic might do the thickness thing again, so it might change it a little bit, but that change will be being caused by something different than a change in the electron pattern. It'll be a change in the density of the electrons because you have more surface area. You're creating a bigger plane for the electrons to be moving back and forth or lining up on. And again, it's more just about their alignment. So my argument is that the slit creates, when the slits are far apart, okay, let's pretend this is far apart, the electrons stay close to home. But when the slits are close together, the electrons migrate into the field. These are trying to do the lightning thing. They're trying to do the spark thing. So they're being migrated by the force into the field. Probably from one side to the other. Obviously there's one side that's plus and one side that's minus. The minus side is the side that has more electrons. Right? So, but anyway, the point is these electrons are moving into the field and they're filling it up as the slits get narrow. And the further apart the slits are, these electrons retract, and so you lose all of this interaction. That's why the pattern is so specific. You go too wide, there's no pattern. Just the right amount of wideness, lots of room for electrons, and they're trying to get across. you go too narrow, no, electrons can't fit anymore, so you have to get pushed out. And you only have a few of them in there. So I think that covers it. And I think it does explain things like diffraction gratings. So what's happening with a diffraction grating is you have the lines so close together that electrons can't really fit in between them, so they're being pushed out to the peripheries. And that's why you're getting only a couple of choices of direction, because there's very few electrons and they're in very specific locations. So there's very few choices in terms of which way you're going to go, which way the electron will move. It's more about which way the electron goes. So obviously you can kind of imagine the electron that's outside of the slit is going to tend to go straight that way or that way, and it's not going to be anything in between. Very few choices. And they're all hitting essentially the same electron that's in the same position, which is the two little tiny slits, or here let's say, and the electron's going to line up in the middle, forward or back from the slit. Alright, I think that's enough of that. So I fixed that, I did that, and so yeah, I think that's all I have. I got to set up the laser, to do the green laser for the good stuff. And so I just not ready. I keep saying get it done, and I just don't get it done. So I'll try to get that done tomorrow. And but I think I fixed where I wanted to fix. Yeah, so it is simple enough now. I mean, this I'm pretty confident. This is all there is. There's just the idea that blue hates blue, and all the blue reflects. So when two electrons come in contact with each other, lots of blue is stuck between them, going back and forth, and has nowhere to go. And the only thing that has an outlet is the red to an electron. And for the proton, it's exactly the opposite. The blues have an outlet, and the reds just bounce off. That's what makes them commons end up repulsive, because they can't get rid of the blue in between them. And that's the game. So I really should be able to do my computer model of it now, because I think I've got it. It's I knew it was going to end up being simpler than I was thinking it was, and it's really this simple. The only interaction that matters is the opposite polarization right term. That's the other one matters, the pressure one holding things together, but I'm just saying the one that's really important. I don't know how to say that. I mean, obviously what's happening when these arrows move back and forth is that these two things will move, so they're going to get accelerated because of these things keep banging into it. That means all the arrows going this way keep getting turned into ones going that way. So you end up with an obvious disproportion of arrows going this way, and that creates acceleration away from each other. Obviously. So I hope that was okay as a clarification. I mean, I will make a video with the light table and try to explain this very carefully. But I think for the people who have been following along, I think you can get what I'm saying here in terms of the general principle. I think so. Okay, so is that enough? I think there was something else I wanted to deal with, but I can't remember what it was. But the diffraction grating thing is kind of interesting. The fact that, but you see, I've seen the double slit experiment done where they'll put something else behind this double slit or the single slit, like another wire or something, and they're not lined up, and they'll still blend into the pattern. They won't be creating a separate pattern, it'll blend into the pattern. And that's not happening. I mean, with diffraction gratings, it seems obvious there's no room in between the two films for a very complex wave interference thing to propagate. It's obviously however the pattern's being created, it's being created really close to the slits, right where they are. And that's obviously is a bit of confirmation of the argument I'm making. It's just terrible today. Just nag. Anyway, till next time, I think that's enough.